In this lecture, we are going to do an example of classification in code using PyTorch. Our problem for this lecture will be to predict whether a patient's diagnosis of breast tissue is malignant or benign. This is a classic application of machine learning, and deep learning especially has made great progress in this field. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to have all our usual imports: torch, torch.nn, numpy, and matplotlib. Next, we are going to load in the data. This data set is part of scikit-learn, so we're going to import the function load breast cancer from the module sklearn.datasets. Next, we're going to call this function and assign it to a variable called data. Next, we're going to check the type of the data variable, since it's not clear what it returns. We can see that it returns an object of type bunch. Luckily, I've already inspected this object, so I know that it acts kind of like a dictionary. In that way, we can call the function keys, and it's going to show us all the keys that we can access from this object. So we see data, target, target names, description, feature names, and file name. So the first two keys, data and target, refer to the input data x and the target's y respectively. So I'm going to call data.data.shape to check the shape of x. Okay, so we see that it's 569 by 30, so that means we have 569 samples and 30 input features. Next, I'm going to print out the targets. Okay, so as you can see, it returns a one-dimensional array of zeros and ones as expected. Now, luckily, even though the targets are just zeros and ones, we can still determine what they mean by printing out data.target names. As promised, they stand for malignant and benign. Next, we can confirm that the length of y is equal to the length of x, 569. Next, note that we can also print out the input feature names as well. So we can see things like mean radius, mean texture, mean perimeter, and so forth. Of course, you're free to look up this dataset online if you want to learn more about it, but remember that we would just like to treat this as a geometry problem. Next, we're going to split the data into train and test. You'll notice that I'm importing things as we go along, since that helps tell the story. But in general, you'll find that it's more conventional to put all the imports at the top. So here we're going to import the function train_test_split from the module sklearn.modelSelection. Then we're going to call this function and make the test set 33% of the original data set. This returns xtrain, xtest, ytrain, and ytest. Then we're going to assign the shape of xtrain to the variables n and d, which may or may not be useful later. Next, and this is important in deep learning, we want to scale our data. The basic idea behind this is that because the output is a linear combination of the input, you don't want one input to have a very large range, say 1 million, and another input to have a very small range, like say 0.001. If this happens, then the weights will be too sensitive when the input has a large range, and not sensitive enough when the input has a small range. So the typical way to deal with this is normalization or standardization. Basically, this just means subtracting the mean and dividing by the standard deviation. Luckily, scikit-learn already comes with a class for this called standard scaler. So we fit transform on xtrain and then we transform on xtest. Remember that it's important not to expose any of our test data to the training pipeline. Next, it's time to do our PyTorch work. As you saw earlier, we first need to build a model object, which is now a sequence of modules. It takes in a list of two modules, linear and sigmoid. The linear layer has an input size d and an output size 1. As mentioned, we want to apply the sigmoid activation so that the outputs are in the range 0 and 1. Next, we are going to prepare to train our model. So we'll need a loss and an optimizer. The loss we're going to use is the binary cross entropy loss, or BCE loss, which is the appropriate loss for binary classification. The optimizer we'll use is called Atom, which is a common default chosen by deep learning practitioners. Next, we're going to convert our data into torch tensors before we enter our training loop. As you've seen before, this involves calling the function torch.fromNumPy. In addition, we still need to convert all the data to float32. One detail you may have missed if you're not accustomed to PyTorch is that we want to reshape the targets to be a 2D array of size n by 1 instead of just a 1D array of length n. In other libraries such as scikit-learn, Keras, and TensorFlow, a 1D array is appropriate, but that's not the case in PyTorch. Next, we have our main training loop. As promised, we're not going to spend much time explaining this because it's pretty much exactly the same as before. There's one small additional detail here, but it's one that doesn't require any new knowledge. Now that we have both a train and test set, we want to be clear about which dataset we use where. So when we do the training portion, meaning a step of gradient descent, we'll want to use the train set, xtrain and ytrain. This involves doing a forward pass, calculating the loss, calling loss.backward, and then calling the optimizer step. So you can see all these here. So we pass xtrain into model to get outputs. We pass ytrain and outputs to get the loss. We call loss.backward and then optimize it as step. But on top of that, we would still like to know the test loss per iteration. This will tell us whether or not our model is overfitting. For example, if we see the test loss increasing during training, then we know that we are overfitting our model. To calculate the test loss, we do some of the same steps, but with the test data instead of the train data. So we do the forward pass, but we pass in xtest instead of xtrain. Then we calculate the criterion with the test outputs against ytest. Finally, we save both the train loss and the test loss in our arrays of losses. Next, we check our loss per iteration. Everything appears to look good, and the train loss is not too different from the test loss, which means our model is not overfitting. Next, we check the accuracy of our model. Remember that, unlike with regression, the metric we care about is very different from the loss function we minimized in order to train our network. Accuracy is simply the number we got right divided by the total number of predictions. In order to get the train predictions, we first pass xtrain into the model, which gives us ptrain. We want to convert the output, which is a torch tensor, into a numpy array by calling the numpy function. These outputs are still probabilities, so we want to call np.round in order to convert them all to zeros and ones. Once we have our predictions, we can calculate the accuracy by doing a point-wise comparison with ytrain and taking the mean. Now, this calculation often confuses beginners. How does this calculate the accuracy? I would encourage you to do a few simple examples in the console on your own if you don't get it right away. Remember that equals equals returns true or false. You'll get true if two items are equal and false if not. This operation happens element-wise, so if ytrain and ptrain are arrays of length n, then doing equals equals will give us an array of length n that contains all trues and falses. So what happens when you take the mean of an array containing trues and falses? What does that even mean? Usually, it only makes sense to calculate the mean for numbers, and clearly true and false are not numbers. However, in Python, true is treated like 1 and false is treated like 0. So if you try 1 equals true in the console, that returns true. And if you try 0 equals false in the console, that also returns true. In other words, this is really like an array of zeros and ones. We have a 1 whenever you got the correct answer and 0 whenever we did not. You should convince yourself that calculating the accuracy is the same as just adding up all the ones and dividing by n, which is also the same as taking the mean. If you don't get it right away, write it down on paper. Next, we do the same thing for the test set to get the test accuracy. The result is that we get about 98% accuracy on both the train and test set, which is very good. As an exercise, here is a nice thing to try. In Keras and TensorFlow, when you do a training loop, you will actually get 2 arrays of data back. One is the loss per iteration for both the train and test set, and one is the accuracy per iteration for both the train and test set. You'll notice that we did not plot the accuracy per iteration here. So for the exercise, you should try to modify this code so that during the training loop, we not only collect the loss at each iteration, but also the accuracy at each iteration. When the loop is done, you should be able to plot the accuracy per iteration. You should see that as the loss goes down, the accuracy goes up. This is usually the case. You might want to also think about what are the downsides of calculating the accuracy at each iteration of the loop.